Okay, 18-12. Apply Coulomb's law to derive the magnitude of the electric field a distance r away from a point charge q and state the direction of this field, of this electric field. Okay, this one's a little bit of math, but not that complicated. The electric field is defined as the force divided by the charge. And the magnitude of the electric field, we're just looking at magnitudes, is the magnitude of the force over the absolute value of the test charge. That's just a definition, a couple of concepts ago. But we know for point charges what the electric force is between 2 point charges. So what we're imagining here is point charge Q here, point charge Q not here, distance r separating these two. And we're interested in the electric field at the location of this test charge. I want the electric field here. All right. Well, this looks like what we talked about with Coulomb's law. If you have two charges, point charge Q1 and point charge Q2, we can figure out the force between those two charges. It's K times absolute value Q1 times absolute value Q2 divided by R squared. It's exactly what we're going to do here. This force now we can replace with Coulomb's law. There's the K. There's the absolute value of Q1, which Q1 in this case is Q. Here's the absolute value of Q2. In this case, the Q2 is Q naught, divided by the distance squared. And this, 1 over Q naught, that's just this piece that's coming along for the ride. Well, now, having put that all together, this is just a combination of various concepts, but a very important combination. Because we get a cancellation, and what cancels in this equation? You say Q naught. Q naught cancels. Hallelujah. And so we end up with a simple relationship for the electric field, a distance r away from a charge q. So now the interesting thing about this is that the Q naught got canceled out. So ultimately, when it comes to finding the magnetic field, it doesn't even matter what the test charge was. Could have been positive, could have been negative. Everything would have canceled out, and you would have gotten an electric field direct magnitude that only depends on the sign of this charge. So if this charge is positive, then this electric field at this point will be in the same direction as the force on a positive test charge. So the electric field from a positive, produced by a positive point charge, points away from that charge. In fact, it's exactly what we saw in this slide here. This must, we've just shown that this must have been a positive point charge. Yeah, electric fields begin on that positive point charge and point out toward infinity. Okay. It's another example. Let me go through it quickly. Given a charge of 15 microcoulombs and a charge of 0.8 microcoulombs, find the electric field at point P. All right. This is 15 microcoulombs. This is 8 microcoulombs. We're going to find the electric field at point P. There are two ways to do it. We can do it using the technique, the short way is to use the result that we got here. Namely, that the electric field at some distance away from charge Q is K times the absolute value Q divided by R squared. That's the easy way. That's down here. We just plug in K, which is 9 times 10 to the 9, times the charge Q, this charge here, divided by the distance squared, and that gives the electric field just like that in measured newtons per coulomb. No big deal. The hard way is to actually first find the force at this point. I can find the force as K Q1 Q2 over R squared, or KQ times Q naught over R squared. That gives the force. And then we can divide that force by the test charge itself, and guess what? We get the same answer as before. This is technique 1 is the action at a distance type formulation. So there's two ways to think about this force. And the same works with objects near the surface of the Earth. If you take a rock, you can say the force of the Earth's gravity on that rock is that the Earth creates a field, a gravitational field that acts down on the rock, and the force on the rock is mg. That's the field concept. Or you can say, well, hang on, I don't even need the gravitational field to calculate this force. I've got Newton's universal law of gravitation, and the force of the Earth, of mass big M, on little m here, is the capital G times big M times little m divided by R squared. That's the action at a distance formulation. So you can calculate it either way. This is just one manifestation of two ways of thinking about the world. Okay, just a concept that electric fields from different sources will add up as vectors. So if you have an electric field that's produced by this bunch of charges A, and you have an electric field that's produced by this bunch of charges B, remember, if you have positive charges, then the electric field lines come out from them. So it's producing electric fields that look like this. And when you're looking at point P, that electric field is going to be in this direction, away from that positive charge. Electric fields always point away from positive charges. A, the same thing, they go away from A. So the net electric field is going to be the sum of those two electric fields. Here's an example of finding, this is a great problem, not that simple, but not that hard once you see how to do it. Two positive point charges. Q1 is 16 microcoulombs, so that's this one here. And Q2 of 4 microcoulombs. Perfect. Are separated by a distance of 3 meters. So there's that 3 meters between the 2 point particles. Find the spot in the line between the charges where the net electric field is 0. You might say, well, hang on, Dr. Edwards, if the net electric field is going to be 0, then the force on a test charge placed at that point will be 0. And I'll say, yeah, you're right. The electric field is 0. And that's where we're going to find this point P, where those two electric fields will cancel each other. Well, both of these charges are positive. So if I remember that, let me just write this down one more time. The electric field is in the direction of the force on a positive test charge. All right, so we imagine putting a positive test charge here and ask what the direction of the electric field is. You can think of it there's a lot of different ways to think about it. One's this way, one's the way we talked about before. The electric field lines created by this positive charge are going to go out like this. So the electric field produced by this charge Q1 and felt by a test charge here will be to the right, away from the positive test charge. Or you could say, you can think of it this way, the electric field at this point, due to this charge, I'm forgetting about charge Q right now, just thinking about charge 1. The field at this point, due to this charge, is in the direction of the force on a positive test charge. So putting a positive test charge, it's positive right here, if you put a positive test charge here, it'll be repelled by this charge Q1. So either way works just fine. I just want you to have different ways of thinking about it. So E1 is to the right, E2, that positive test charge would be repelled by charge Q2. So Q2 would push that positive test charge to the left. Okay, so clearly the two electric fields are opposite each other. One's to the right and two's to the left. And if we want them to cancel each other, we better set their magnitudes to be equal to each other. This is the magnitude of the electric field produced by charge 1, this guy here. This is the magnitude of the electric field produced by charge 2. And if those magnitudes are the same, the directions being opposite, then they'll cancel. The two fields will cancel. Well, we now know how to deal with electric fields, K, Q over R squared. E1, that's easy. I just have K. I'm not going to actually plug in its number here for a reason that you'll see in just a minute. Q1 is 16 microcoulombs. That's this number here. Divided by the distance between Q1 and the point of interest, P. We're going to call that distance D. That's the distance between this charge Q1 and this positive test charge. That's D squared. That's E1 that we put over on the left side. E2, well, it's also going to be K. It's going to be charge Q2. That's 4 microcoulombs. That's this number right here. And then we're going to divide by the square of the distance between Q2 and this positive test charge. Well, what's that distance? Well, we know that the distance between the two charges is 3 meters. And the distance between charge Q1 and the test charge is D. Therefore, the distance between charge Q2 and the test charge must be 3 meters minus D. And so that's what we see here, distance between them. Now we have a beast of an equation to solve, but luckily we didn't plug in the values of K and they cancel each other. So that's a happy day. And but how are we going to solve for D? It looks almost hopeless, but it's not. What we can do is cross multiply. We have two fractions, one fraction on the left side and one fraction on the right side. To solve that equation, you can cross multiply. Multiply the numerator on one side by the denominator on the other side equals the numerator on the second side times the denominator on the first side. So this, let's see, how did I actually do this? Oh yeah, okay, so 16 times 10 to the minus 6 divided by, if we divide both sides by 4 times 10 to the minus 6, the 10 to the minus 6 is canceled. We get 16 divided by 4, and that's 4. So then we just replace this with 1, this piece here with 1, and we replace this with 4. And then we have 4 times this, so that's cross multiplying these two. 4 times 3 meter minus D, quantity squared, equals this times that, D squared times 1. And so, can you solve that? And the answer is for sure you can. Use the quadratic formula. So you can rewrite this as, let's see if we have any space here, 4 times 3 meters minus d. Oh, actually, the simplest way is not to use the quadratic formula. The simplest way is just to take the square root of both sides. By far the simplest. So now if you take the square root of the left side, you'll get 2. Square root of 4 is 2. Square root of 3 meters minus d quantity squared is just 3 meters minus d. And that's equal to plus or minus d. And how do we get that? The square root of d squared is just d. But whenever we take the square root of both sides of an equation, we have to put a plus or minus out in front. That's why the plus or minus here. Because we could have had minus times a minus squared equals the same thing as a plus times a plus. So ultimately now we've got 6 meters, this is a very long example, sorry about that, times 2 times 3 meters is 6 meters, minus 2 times d equals plus or minus d. And now we're trying to find d. 6 meters equals 2d plus or minus d. I've added 2d to both sides of the equation. So now we actually have two solutions. If we take the plus sign here, we'll have 3d divided by 6, and d will be, 3d equals 6. And 6 divided by 3 is 2. There's one solution. If you take the minus sign, 2d minus d is our old friend d. Therefore, d would be 6 meters. So we actually get two solutions out of this problem. And so let's go back to the question and see which answer pertains. Find the spot on the line between the charges where the net electric field is 0. Well, we found two answers. One, d of 2 meters. Here's the distance between the charges. Here's d of 2 meters. So that d is definitely between the two charges. If we use the 6d, that would say that d is clear out here, double the distance between the two charges. So it's outside the region between the two charges. So the spot on the line between the two charges would be this 2 meters. So that's a complicated example. Congratulations for making it through it. A conceptual example, symmetry in the electric field. A lot of examples needed here. Point charges are fixed to the corners of a rectangle. Two different ways. The charges have the same magnitudes but different signs. So in this case, there's one negative charge. In this case, there are two negative charges. 1, 2. Consider the net electric field at the center of the rectangle in each case. Which field is stronger? Well, let's look at it. And let's look at the field in pairs. Let's look at 1 and 3 first on this one. What's the direction of the field produced by 1 and felt at point C? You say, well, I know that. The electric field produced by a positive charge emanates out in all directions from that positive charge. So the electric field looks like this. So the electric field line that comes and intersects this point here is going to be pointed in this direction. That's E1. The electric field produced by this guy, Q2, goes out in all directions. And the particular field line that I'm interested in, the one that crosses the point of interest, is coming out that way. So this is E2. I'm sorry, E3. If this charge at point 3 and this charge at point 1 have the same magnitudes, then what can you say about these two electric fields? You're right, they cancel. So E3 and E1 cancel each other, and these guys don't have anything to say about the electric field at the center here. It's the same as the previous example, where we tried to find the spot between two positive point charges where the electric field would be 0. Same thing happens here, except now the two charges have the same magnitudes. And so the point, instead of being 2 meters out of 3, would have been right smack dab between the two charges. So these guys produce no electric field here. What about these two guys? Well, this guy produces an electric field in that direction. We'll call that E4. Remember, the electric field is away from that point, that positive point charge. This negative charge, we haven't talked about that much yet. This negative charge produces electric fields that go into it, not out of it. So electric fields for negative charges point into the into those charges. So this is the electric field that this negative charge produces. It's pointed that way. Which one of these electric field lines intersects the point of interest? You say, well, the one that's right about here. So E2 and E4 will combine together to form an even bigger field, double the magnitude of either of them. So this is the total field. Let's look at this case here. First look at 1 and 3. And now we can do this one faster because we pretty much understand what's going on. 3 produces an electric field at this point that's pointed in this direction. The electric field is away from positive charges. This negative charge produces an electric field in the same direction. Why is that? Because the electric field produced by a negative charge points toward that negative charge from wherever it is you're interested in. What about over here? Well, the same thing here happens between 2 and 4 that did over there. We get a E2 and an E4 that point in the same direction. So if these two are the only guys acting, then the net electric field would be in this direction, E2, 4. That's the fields of both of those two. But we also have these other two that don't cancel anymore like they did over here. And we get an electric field, combined electric field from 1 and 3 that's in that direction. If we add this vector to this vector, then we can use the parallelogram addition approach, and the total electric field is going to be this. Clearly, that vector is going to be longer than this vector. This total vector here is the same as this E24, but then we also have this other one to add up. So this one has a stronger field.